Hello, everyone. Hope you're doing well. And it's time for another lecture in advanced calculus. And we'll start with an elementary discussion about something that you've probably encountered in your previous math courses. And this is about the irrationality of the number square root of 2. Now, let's try to sketch the proof of the following theorem, which says that this number, square root of 2, is irrational. Of course, we know that this can be approximated in decimal places, rather in using a real number. But first, let's consider the following theorem that says that there is no rational number whose square is 2. Now, to prove this one, let's briefly recall the definition of a rational number, and recall that a rational number can be written as the quotient of the form P over Q, where P and Q are integers. And equivalently, the theorem can be stated in this way. There are no integers P and Q such that the square of the quotient P over Q is equal to 2. Now, to prove this, let's do proving by contradiction. So by contradiction, suppose such integers P and Q exist. And let's make a further assumption. Let's assume that the integers P and Q have no common factors, because otherwise we can just cancel out the common factors between P and Q. So in other words, we want the quotient P over Q written in lowest terms. And then, since this equation holds, then note that we can also write this one as P squared equals 2 times Q squared. Now, notice we can write the square of P as a multiple of 2. Then that means that indeed P squared is actually even. And then because P squared is even, then the integer P, which is the square root, must also be even. Note the hint here is this one. Then, because P must be even, we can write P as a multiple of 2, which is equal to 2R for some integer R. Then, if we substitute this expression for P here, what we have is this one. That's the square of 2R equals 2Q squared. And simplifying that one or expanding that one, that's 4r squared equals 2q squared, or we have q squared equals 2 times r squared. By the same argument, q squared is, notice it's actually a multiple of 2. Then q squared is even, and therefore the integer q must also be even. Now, earlier we concluded that p is even because now p and q are both even, then p and q both have a common factor of 2. Now, this contradicts the previous assumption that they must have no common factors. And therefore, we arrive at the contradiction. So therefore, indeed, the theorem is true. Now, note that in geometry, the irrational number square root of 2 exists. In fact, the number square root of 2 can be thought as the length of the square whose sides are both equal to 1 unit. And so therefore we can write square root of 2 in terms of decimal numbers. Note that here we're only operating in terms of rational numbers, but seeing this observation, we see that the rational numbers do not suffice to describe geometric concepts such as length. So therefore, when we, and of course, the idea of length exists in nature. So therefore, in order to describe concepts in geometry, which are all related to concepts in nature, we need a larger, sorry about that. We need a larger set of real numbers. And that brings us to this. Now, before we describe this larger set of real numbers, first by notation, when we say the natural numbers, we refer it as with the symbol bold N. And just to enumerate, the not natural numbers are consistent of 1, 2, 3, and so on. And note that in natural numbers, we have the addition operation is well defined. That means the sum of two natural numbers is also a natural number. But in order to have a well-defined, but note that in order to have another well-defined operation, which is the subtraction. But first, before that, I want to also mention that also the multiplication is also well-defined. And in order to have a well-defined subtraction, we need a larger set of numbers, and that brings us to integers. Where throughout this course, we denote as big the bold Z, which is equal to this one. Now notice here we included the number 0. We can't include it here in natural number because otherwise the subtraction will not be well defined, because we can see that with integers, we now have not just plus and times, but also the subtraction, which is well defined. So therefore, if you subtract two integers, then you will also get another integer. Now, aside from that, we also have another operation in arithmetic, which is division. So therefore, to have a well-defined division operation, we need a larger set of numbers, and that brings us to the rational numbers. And throughout the course, we describe it as bold Q, which is the set of all fractions written as P over Q, where P and Q are integers with Q not equal to 0. Now, for the set of rational numbers, the addition, multiplication, subtraction, and division are all well defined. That means the quotient of any two rational numbers must also be a rational number. Not only that, in the set of rational numbers, we also have an additive identity, which is 0, which is also in the set of integers. And we also guarantee the existence of a multiplicative identity. And this allows us to have a well-defined definition of division. And in fact, what we can actually conclude here is that because the set of rational numbers satisfy these following properties, we can also describe in algebra that the set of rational numbers is a field. Okay. And also an important property of the set of rational numbers is known as the natural ordering set of rational numbers, which goes like this. Given if you have two rational numbers, say R and S, exactly one of the following is true. That is, first, either R is less than S, R is equal to S, or R is greater than S. Now, because of the natural ordering in the set of rational numbers allows us to locate rational numbers in this number line, you have 1 here, plus 1, this is 2, and so on. Okay, so all rational numbers can be found here. So for instance, this is 3/2 or 1.5. Okay, so the idea now is this. What are those numbers that cannot be that are not rational, but should be found here in the real number line? And that brings us to the numbers which are not rational, and that is the irrational numbers. Now, for instance, if we go back to our favorite irrational numbers, not that square root of 2, and we estimated as 1.414. So if we approximate 1.414, we can assume that it's somewhere here. That's 1.25. So it could be somewhere here. Okay. So after describing the rational numbers in the number line, what we actually notice is that the irrational numbers fills up the holes or gaps in the number line. This fills up the gaps in the real number line. And that brings us to describing the set of real numbers. So therefore, the set of real numbers can be described as the union of rational numbers and the set of irrational numbers. Note that irrational. So this is how we can actually describe the real numbers. And also, we also need, now in the previous notice that we've shown that square root of 2 is irrational by using the definition of a rational number and then arrive at the contradiction. Now note that there are irrational numbers which cannot be described in terms of the square root. For example, the log of 2. And we can also have the cube root of, let's say, 5, which is not a square root. So you have transcendental numbers as well. So what we need to do is to describe the set of real numbers that encompasses all sorts of irrational numbers. So from the previous description, we can have this following Venn diagram. So what we can have is, first we have this smaller set of natural numbers, and this is contained on this larger set, which is the set of integers, and in turn, the set of integers is contained in the next larger set, which is the set of rational numbers, and in turn, the set of rational numbers are contained in this larger set of real numbers. So as you can see, a set of natural numbers is contained in Z, In turn, Z is contained in Q, and in turn, Q is contained in R. So that's the aim of analysis.